This is example 3.2 in your text. If you read example 2.5, this is just an extension of that. For a continuous random variable, consider the 100 kilogram load in example 2.5. The load is equally likely to be placed anywhere along the span of a beam 10 meters long. What we want to find then is the PDF and the CDF, what they look like for this case. So the PMF, or excuse me, PDF in this case, because it is a continuous problem, it's a continuous random variable x. We write out that the PDF fx of x is equal to a constant because it's equally likely to be placed anywhere along the 10-meter beam. So from 0 to 10, if x takes on any value in between here, 10 or equal to or less than 10, it's going to be equal to some constant probability. Otherwise, it's going to be equal to 0 because it's only a 10-meter long beam, so the load cannot be placed beyond 10 meters. So we're bounded here. So we want to find what the PDF looks like, so we need to find out what this constant c is. So we just simply take the integral from 0 to 10 of the PDF dx, and we know that this has to be equal to 1 because the area underneath the probability density function, PDF, is equal to 1. That's exhaustive of our sample space, so it has to be equal to 1. So this is really the integral from 0 to 10 of that constant c dx is equal to 1. So we evaluate cx at 0 and at 10 equal to 1, and we end up with c is equal to 1/10. So the plot of 1/10 is the PDF over the length of the beam. So the PDF takes on this shape of a curve, and the area underneath here is exactly 10. It's exactly 1. Right? Because the height is 1 by 10 and the length is 10, so therefore that area has to be equal to 1. To find what the CDF looks like, well, we apply the definition that the CDF fx is equal to the integral from 0 to x of c dx, where this is our probability density, and this is equal to cx, and this is x over 10 for values of x between 0 and 10. It's going to be equal to 1 for values that are greater, x greater than 10, and equal to 0 for x less than 0. So the plot of the CDF is given by figure 3.2b, where it's 0 at 0, and then it increases linearly all the way up to 1 at 10, and then it flattens out. It stays 1 for any other value. So this gives us what the CDF of our random variable x looks like for this problem.